The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Hello and welcome to Science for the People. I'm Desiree Schell, and today we're going to be talking about cognitive biases, personality flaws, and other inherent facets of being a human and how they affect scientific understanding and discovery. A little later, we'll speak with Sean Roberts and James Winters about some things that you should know about correlational research. But first, let's visit with Dr. Morton A. Meyers. Hello and welcome to Science for the People. I'm Desiree Schell. My guest is Dr. Morton A. Meyers, Distinguished Professor of Radiology and Medicine and Emeritus Chair of the Department of Radiology at the State University of New York at Stony Brook. His classic Meyers Dynamic Radiology of the Abdomen, Normal and Pathologic Anatomy, now in its 6th edition, has been hailed as the book that revolutionized abdominal radiology. But he's here today to talk about his new book, Prize Fight. Welcome, Morton.
Thank you.
Now, your book covers a number of cases of scientific discovery, focusing on examples that don't exactly paint the researchers in the best light, necessarily. So when did the pursuit of scientific discovery switch from being presented as this very noble and selfless endeavor to the far more realistic way that includes all the egos and bad behavior?
The thought occurred to me in writing the book that it might be worthwhile to trace the lineage of popular histories of scientific research, particularly over the 20th century. And the first example that I use is that of Aerosmith by Sinclair Lewis, written in the 1920s, in which he describes the great nobility of scientific research, purely for its own contribution to knowledge and its own feeling of self-satisfaction. The year after that was published, a book called Microbe Hunters was authored by Paul de Kruif, who was a researcher at Rockefeller Institute in New York City, and that is highly laudatory to a whole series of described basic researchers in bacteriology and so forth. These people are portrayed in an almost saintly manner. But then this whole thing got blown apart in the 1950s by a book by James Watson called The Double Helix, which garnered he and his fellow researcher Crick eventually with a Nobel Prize, in which they made the groundbreaking breakthrough of describing the structure of DNA. But that book indicates the innate coveting of recognition and competitiveness and occasionally deceit in the scientific endeavor. The book became hugely popular and has now sold over 1 million copies. And then, most recently, perhaps 10 years ago, a book came out that was very popular by Allegra Goodman called Intuition, in which she portrays two researchers at a major university who are willing to sacrifice some degree of integrity for expediency and self-interest in promoting their new claimed discovery, even though they recognize that it may not be completely true as they describe it. So we can trace the transition from the popularization of scientific research as one of the most noble pursuits to finally recognition of the human element and the drama and the personal need for recognition behind scientific research. So that is now portrayed in not only books but movies, television series, and other forms of media. As a matter of fact, the current issue of The Economist, a weekly periodical from Britain, its cover story is on elements of flaws in the scientific endeavor, especially in regards to the old axiom that science is self-correcting, which it certainly is not, and they point out all the flaws now in the system. Now, I believe that if one understands the flaws in any system, you understand the system much more clearly and certainly more accurately. So science is now being recognized as not only dispassionate and objective, but there's human nature involved, unchanging human nature, of course, which sometimes taints the picture of the nobility of science. And one of the more recent true incidents that brought this to people's attention was the argument over whether measles vaccine, for instance, was the root cause of the increasingly recognized instances of autism. And a major article proclaiming that was published by The Lancet, a very prestigious English publication, and certainly influenced many mothers to keep their children from getting measles vaccine. But what it led to was an epidemic of measles, unfortunately. And it took perhaps 20 years before the co-authors of that article retracted all of their claims and their authorship because nobody could duplicate the results, and it was finally declared a pure instance of fraud. So the pressure on the scientific researcher in the era now especially of diminished funding for research, in the need for establishing one's prestige as an aspect of human nature, of tenure and salary in an academic setting, leads to an increasing incidence, unfortunately, of what's called euphemistically scientific misconduct. And again, as I say, if one understands that, one can understand the greater spectrum of what is meant and what influences scientific research.
Well, you write at length. Although, as you said, scientists are all human and they're all individuals, there are some sort of general themes that do drive them to their breakthrough discoveries.
Well, by themes, there's a variety of themes. And what I try to do is to pick up the thread that runs through many of the more recent scientific discoveries so that a pattern emerges from which we can draw valid conclusions. And there's a host of examples that can be revealed. And what I've done is go through archival material at universities. I've conducted a host of interviews, including Nobel laureates. By the way, the interesting thing about Nobel laureates is that if you speak to them before they win the Nobel Prize, they're, of course, much more guarded. Whereas after the prize, they can be more relaxed and can be refreshingly candid about what really happens behind the curtain. I think the way the general public receives these scientific advances or reads about Nobel Prizes as if it comes from some distant authority up a mountain or something, has the perception that scientists are dispassionate and objective. But the thread that runs through is the drive for recognition. Scientific research is a highly noble endeavor, but involving humans, not only is the need to contribute to knowledge and to perhaps uncover a law of nature, but certainly associated with that in a scientific researcher is the need to be recognized, especially by one's peers. That's one of the highest goals reached is approbation by other recognized people in one's field. Therefore, what's happening, especially recently, I think, are elements of scientific misconduct. And it's being recognized now that when I say scientific misconduct, the word covers such examples as fraud or fabrication of data or plagiarism. But if you trace this now in the last, I would say, 15 years, there's been at least a tenfold increase in retractions. Retractions means the forced withdrawal of spurious articles or articles that have been proven to be spurious based on scientific misconduct. And some scientists are repeat offenders. Like, take the example of a Dutch psychologist recently, Diederik Stapel, who committed academic fraud in over 50 published papers. Then there's a South Korean plant scientist, Young-in Moon, who faked other scientists' email addresses so he could review his own papers. Very, very creative. Or Jan Hendrik Schoen, a physicist at Bell Labs, who published a peer-reviewed paper every 8 days. Every 8 days, the man came out and had a scientific paper published.
No red
Cleverly
flags
based,
there at all.
not at all. And listen, this involved his supervisors. Bell Labs was recently, at that time, bought out by Lucent Technologies. So, new company, new administrators. They wanted to establish and continue the sheen of research coming out of this laboratory. I mean, after all, historically, Bell Labs research has won several Nobel Prizes over the years. It involved the journals who were hungry for publishing what they thought were breakthrough articles, and involves a peer review system, which notoriously does not have much accuracy in detecting fraud in published and papers that are being reviewed and so forth. So it's a confluence of factors. But Schoen was very clever because he based his fabrications on anticipating where his field of nanotechnology would likely develop. So he fabricated data, but he had a very clear idea of where his field would likely in the future, most likely by others, truly make contributions. But that's like shooting an arrow into the side of a barn and then drawing a bullseye around it. So lifting the veil on scientific discovery reveals to us the human dramas that underlie several advances. Worthy certainly of prizes, but what's of interest is to me, and I think to the general reader as well as to the scientific community, is understanding the human dramas behind this. Because to be first is we live in a winner-take-all society. And to be first is to garner recognition and rewards. To be second is to be forgotten.
You're listening to Science for the People, and I'm joined by Dr. Morton A. Meyers. We're talking about his book, Prize Fight, The Race and Rivalry to be First in Science. Now, all the examples that you brought up are very clear examples of fraud, but unfortunately things get much more murky when we're talking about recognition as the first in a field, because it's often difficult to discern who the first person was to have that radical idea or to interpret just how meaningful a new idea might be. And why is that?
I think you're touching certainly on a root problem throughout scientific research, because the impulse, the need for recognition involves a priority. In other words, who was the first to make a discovery? That's what's meant by priority. And everybody in writing something or contributing a bit of knowledge wants to be recognized as having established priority in that uncovering. Accompanying that is proper credit. But the problem is very complex. And the Nobel Committee itself faces every year very difficult decisions in order to establish who deserves the prize, who deserves the recognition of priority, and who gets the credit. And in many endeavors, there's a whole host of antecedents, sometimes leading back decades, if not actually centuries, that have presaged the development of the field until perhaps somebody has a particular epiphany that launches it both for validity and for contribution to mankind's benefit. And the criteria for establishing credit is not clear. It often varies from case to case. Well, the prime example, perhaps, is the idea. I mean, every school child, when you ask him or her who discovered America, will say Christopher Columbus. But we know that Christopher Columbus didn't realize what he had discovered. He thought it was India, rather than islands in the Caribbean that he kept bumping into. And so when he was there, he didn't know what he had discovered. When he came back, he didn't know what he had discovered. And yet he is credited with the discovery of America. So the question arises, who gets the credit? Who deserves the prize? Is it the person who first has the idea? Is it the person who develops it in one way to make it more accurate? Is it the person who nurtures it so that it's embellished and is enabled to be brought to mankind? Is it the person who figures out the meaningfulness of a set of observations or findings and is able to tie it all together into a new theory or a new invention? So all of these things are somewhat clouded and forms the basis for rivalry and the surprisingly frequent contentious and bitter battles between researchers over what they would conceive of as false attribution and contribution. There's a host of these examples throughout the history of medicine, the history of science, sometimes lasting 30 years, sometimes lasting 50 years, where the acrimony continues and a person, a researcher feeling he didn't get due recognition, feels that he's living in anguish for the rest of his life. Recognition, after all, is an innate need of people. I mean, if you go to a playground and you see a little kid climbing up the monkey bars, he's yelling out to his mother, "Mom, look at me, look what I'm doing." Everybody wants to be acknowledged. Scientists are as open to that as you and me. And therefore, to establish themselves, they're often open or to be persuaded to assert their action and manipulation. They are, after all, human. They are not supermen. And to understand that is to understand scientific research.
But there's also a number of almost simultaneous discoveries throughout history, aren't there?
Yes, and that's an interesting aspect of it. The term used in that regard generally is the German word Zeitgeist, which literally means the ghost of the time. But often advances in a field happen so that it's what's called in the air. Everybody is aware of it, and it would take then an astute mind to propel it to the next stage of uncovering a basic law of nature, for example. Science. A classic example is the telephone, for instance. So Alexander Graham Bell presented his idea. He went to the patent office and met there another man. His name was Elisha Gray, who also had conceived of the telephone. So this is an example of simultaneous discovery. Bell worked out a financial arrangement with Gray, who was happy with it, and Bell went on to be recognized as the inventor of the telephone. But it is the fear of simultaneous discovery, on the other hand, that can motivate, if not inflame, a researcher. If he knows that a rival is working on the same area, that adds a competitive edge and propels him to work even harder and more assiduously and longer and so forth. But the same idea, for as a young researcher knows that the deck is somewhat stacked, that funds will continue to be given to a more mature, recognized researcher, and he may therefore see the reality, in a sense, of playing it safe and just following conventional ideas and, in the publish or perish rubric, simply not go for the head of the comet, but simply follow the tail of the comet.
This is Science for the People, and I'm here with Dr. Morton A. Meyers to discuss his book, Prize Fight, The Race and Rivalry to be the First in Science. And we'll be back with more after these messages.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Desiree Schell, and my guest is Dr. Morton A. Meyers, Distinguished Professor of Radiology and Medicine and the Emeritus Chair of the Department of Radiology at the State University of New York at Stony Brook. We're talking about his book, Prize Fight, The Race and Rivalry to be the First in Science. Can we talk about maybe just one fairly stark example of how this played out in the real world? The development of the MRI was fairly messy, to say the least.
Yes, messy and tempestuous, I would say. But it provided me a very challenging eyewitness experience, which really led me into the whole idea of prize fights. His name was Paul Lauterbur. who was an expert in a chemical procedure that was called nuclear magnetic resonance, NMR. This is a technique that had been used for decades by chemists, which enabled them to work out the structure of various molecules and so forth. But what happened is that another researcher, and when I first came to Stony Brook, I recognized that this field had the potential of a burgeoning advances, and I gave to Paul a conjoint appointment in radiology as research professor of radiology. But several years before, another researcher at Downstate Medical Center in Brooklyn had published that the technique of NMR also could distinguish the differences between normal tissue and cancerous tissue. So this article really established the biological basis and indicated the potential medical applications of this technique that had been used by chemists. Lauterbur, because of his expertise in the technique, certainly knew of that article, and one evening had a eureka moment, an epiphany, that he figured out how to derive an image from this technique. And after all, both radiology is an imaging specialty, and this further indicated how it perhaps could be really fully appreciate the potential use of using this technique for imaging, its use to medicine. But what is notable is that in his notebook, first explaining his technique in order to establish his priority, he acknowledged the other researcher's paper and also used it as in his own grant applications. But for the next 12 years, Lauterbur and his multiple subsequent publications never acknowledged the other researcher, never cited him in his references, never made a side acknowledgement of him, always trying to advance his own reputation in having established the technique of imaging. So the other researchers' funds got cut off. Lauterbur was on committees at the NIH, the National Institutes of Health, the major source for funding of academic research, and the other guys' applications would not be accepted. There were other movements toward ruses and stratagems that each used to overcome, but Lauterbur's original article appeared in Nature in 1973, and 30 years later, with the development of computers and the introduction of CAT scans, another form of imaging but using radiation, and then finally MRI machines were produced by the major commercial vendors. In 2003, Lauterbur was awarded the Nobel Prize, much to the other researchers' consternation, who then took out a series of full-page advertisements in the New York Times, the Los Angeles Times, the Washington Post, and even Swedish newspapers in an unprecedented attempt to persuade readers, including scientists, physicians, and even the Nobel Committee itself, to reconsider and include himself for the Nobel Prize. This was not done, perhaps understandably, and the bitterness continued for over a period of 30 years.
But the evidence was on the other researcher's side. Damadian?
Damadian was his name. Raymond Damadian, yes.
So the evidence was on his side, and that was actually borne out through the courts.
Well, let me explain also. Yes, you make a very good point. The Nobel Committee is always very careful in how they phrase the wording of the prize. In this case, they tailored the wording to indicate magnetic resonance imaging. So Damadian did not, in that sense, develop imaging, but did establish the biological basis of using the method to distinguish the variety of tissues within the human body, including infections and cancer, most notably. Several years after the beginning of this bitterness, Damadian developed further applications and won several patents, and finally sued the major commercial vendors, including GE, Hitachi, Philips, Siemens, and so forth, for violating his patents. That went up to almost the level below the Supreme Court of the United States and was settled in Damadian's favor. That basically legally established his proper claim to having initiated an understanding of the technique and its potential medical applications. So I do feel very strongly that Damadian deserved the Nobel Prize as well. The prizes can be given to three people. So in this case, it was given to Paul Lauterbur at Stony Brook, and it was given to Peter Mansfield from the University of Nottingham, who also contributed significant advances for the understanding of application of MRI, but they purposely left the third slot open. So I do feel that Damadian deserved that third slot and proper acknowledgement, but there was another element, unfortunately, that entered the picture. Damadian is a creationist. He believes that the earth was formed 6,000 years ago, and he believes almost in the literal truthfulness of the Bible. So there is a feeling in some quarters that he compromised what many people would consider the basis of science and scientific judgments, and some people feel that entered the considerations of the Nobel Committee. That can't be analyzed beyond that kind of speculation. Damadian, I think, suffered an injustice in this case.
So I assume that there are many other cases like this, ones that we never hear about, because it's kind of unseemly, but also because making an issue out of priority has definite long-term effects on one's career.
That's absolutely true, and I think many of the conflicts are just simply smoldering in an individual's mind and isn't brought to popular attention. But one other example is the case of the discovery of streptomycin, the first antibiotic useful against tuberculosis. This occurred in the 1940s, shortly after the discovery of penicillin, for instance, which was the first wonder drug. And this involved a internationally renowned professor by the name of Selman Waxman at Rutgers University in New Jersey, and a 23-year-old graduate student by the name of Albert Schatz. Waxman had spent years searching, he was an expert in soil bacteria, soil microorganisms, and he spent years developing protocols for the elaboration of products yielded by these soil bacteria, and then directed and focused his attention particularly on the search for antibiotics. And he came up with several, but they proved, unfortunately, too toxic for human use. But he was on the right trail, certainly. And many of his young graduate students worked on this pursuit. And then what entered the picture was Albert Schatz, 23 years old, and Waxman assigned him the task of further exploring soil bacteria for antibiotics. And astonishingly, within only 3 months, Schatz came up with a chemical extruded by a type of soil bacteria that was proved useful against infections that penicillin didn't cover, but also particularly against tuberculosis. And indeed, he was the senior author on several papers from Waxman's laboratory to that effect, as well as being a co-signature on the patent for the discovery of what subsequently was known as streptomycin. He went on to pursue his academic career at other laboratories and didn't really show any further interest in the development and certainly not in the commercialization of streptomycin, whereas Waxman had a more visionary approach, and with his relationship to Merck, a major drug company in New Jersey, who produced the antibiotic and from which royalties were derived, had visions for using the money to establish an Institute of Microbiology and a Foundation for Microbiology. Finally, Schott felt that he was not only being ignored, but that, contrary to his expectations, that money was being derived from this discovery, and sued Waxman. This also at the time was unparalleled. It hit the major newspapers, including the New York Times and so forth, and it was finally settled out of court in Schatz's favor. Waxman's attitude in several letters exchanged between the two was that Schatz was only his, quote, his hands, and was only a, quote, a cog in the machine because of Waxman having established the protocols. And, I mean, the idea was if Schatz hadn't discovered it, one of his other graduate students would have. But nevertheless, because of the publicity that the case garnered, Schatz was basically blackballed, was blacklisted throughout the whole entire scientific community in this country. No other laboratory would hire him. He was considered a whistleblower who would only be an irritant in any other lab. So he was forced to flee to Chile with his family, and never again was offered a job in an academic research laboratory. He anguished over this for many, many years. The man died several years ago in his 80s and carried this cross with him, feeling that he suffered a severe injustice, that he deserved greater recognition for this, if not retroactively to share in the Nobel Prize, and lived a very unhappy life, feeling that he had been handled very poorly. So that's the other side, you see, to the Lauterbur-Damadian episode. Lauterbur-Damadian were two senior researchers with intense rivalry, whereas in the Waxman example, this is a conflict between the senior researcher and a young graduate student in his laboratory. Graduate students today do much of the hands-on research in laboratories around the country, and they're underpaid, overworked, and generally quite unhappy. But they are working toward a PhD, which they hope will springboard them into their own laboratory at some point of time. So the two cases are very complementary and give us great insight into the issues that arise, the issues of authorship, of credit, of priority, of acknowledgement, of stratagems that are used by each party to overcome what they consider injustice and so forth.
And I guess my biggest question is about cases like this. Do they actually push scientific discovery, this kind of hyper-competitiveness that's bred, or are they detrimental to progress? Because in the case of the MRI, it almost seems like competition might have stalled the process.
I think it's a double-edged sword, to tell you the truth. On the one hand, to know that there's rivalry spurs somebody to really put their nose to the grindstone and work harder. In the case of Damadian, for example, the development of research came to such a point that it was clear the next major jump would be to image the human body. Damadian and his two loyal, dedicated postdocs spent a year of working virtually every day, perhaps taking an occasional Sunday off, 18 hours a day, to build their own MRI machine. I mean, there hadn't been commercial development yet of those machines. So they bought it from spare parts that they picked up here and there, labored intensely for a year at this Herculean effort, built an MRI machine. Damadian offered himself to be the first human to be imaged within the machine, but parts of the material that was used for the imaging capabilities didn't fit him, and so one of his two postdocs finally volunteered and had to sit within the machine for 4.5 hours and generated the first image through the thorax of this young man's chest that showed, through the process of MRI now, showed his heart, his aorta, his lungs, his ribs, the muscles of his chest wall, and so forth. It's rudimentary. The image is rudimentary by our standards today, but it was a major breakthrough. And it's after that as well. The point, however, is that such competition, such rivalry, such potential bitterness can stifle innovation. A young researcher, as I indicated, would say, my odds of doing a breakthrough of this magnitude are extremely slim, and I therefore will just polish what's been known a little bit, contribute perhaps an article, shine an edge here and there, and basically innovation is stifled because of that.
Morton, great to have you here. Thanks very much.
Thank you.
And you can find a link to Dr. Morton A. Meyers and his book Prize Fight on our site at scienceforthepeople.com. You're listening to Science for the People. We'll be back to talk with James Winters and Sean Roberts about the complexity of correlation research and cultural traits after these messages.
On the next episode of Science for the People, we're discussing some science surrounding our favorite adult beverages. We'll revisit our interview with Dr. Charlie Bamforth, professor of malting and brewing sciences at the University of California at Davis, about the chemistry of the beer brewing process. And we'll speak to researcher and winery owner Robert Hodgson about his study exposing the shaky science of wine tasting. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Desiree Schell, and I'm joined by two guests for this segment. The first is Sean Roberts, a researcher at the Max Planck Institute for Psycholinguistics. He looks at how individual cognition and conversational interaction are related to population-level phenomena. Welcome, Sean.
Hello, how's it going?
And James Winters is also here with us, and James was formerly a student at the University of Edinburgh, graduated with an MSc in the evolution of language and cognition, and right now his focus is on writing about language and cultural evolution. And both Sean and James blog about language evolution at replicatedtypo.com. Welcome, James.
Hi there.
So you two have authored a paper titled Linguistic Diversity and Traffic Accidents, Lessons from Statistical Studies of Cultural Traits. Can you just walk us through that?
Yeah, sure. So we were noticing a trend in linguistics, which is our field, and sort of the studies of cultural phenomena in general, that more and more papers were coming out that had some fairly interesting hypotheses, and then using very large-scale cross-cultural databases to demonstrate statistical correlations as the sort of the evidence for these hypotheses. But there were lots of problems with these approaches that we saw.
So one of these problems that we often see is these cultural studies tend to take a sample which is sort of a single slice in time, and as a result, we don't have much time depth for these cultural features, which is problematic because it essentially discounts the historical relationships between cultures. And consequently, because of this, if two languages are closely related, then it's common sense that they're more likely to share the same features and others than, say, more distantly related languages. So as a result, we should expect to see cultural features correlate in languages which are closely related. And a problem with these studies is they don't often control for these factors.
So we could give you an example. The title of the paper comes from a correlation that we found between the number of languages that are spoken in a country and the number of traffic accidents. So the more languages that are spoken, the more traffic accidents that happen. And this correlation you can control for things like GDP, population size and density, the amount of roads in the country, in the amount of migration, or the distance from the equator, or all these kind of different things that you might think might have an effect. But the correlation remains robust. So there seems to be some sort of link between these two things. And the most sort of intuitive thing to do is to think, well, maybe they're linked somehow. Maybe if you have a lot of languages that are being spoken, then there are lots of different languages on road signs, and that takes longer for people to read, and so they crash, and you have all this sort of neat story to go with this correlation. But we think that's a dangerous idea because it's not really controlling for the different ways that languages and cultures are related historically.
Yeah, and the problem, if I can just add something else to that, is that the major problem with this is that it's quite easy to come up or discover correlations first and then attribute a hypothesis to it afterwards. And I mean, we see this. I mean, I'm assuming we see this quite a lot in these correlational studies where they found this nice correlation between feature X and feature Y, and then you can justify the correlation through telling a nice story. This isn't to say this is necessarily wrong approach. And I think there are studies that have done this, and they've then followed it up with other methods such as experiments. But I think sometimes it's not clearly stated that when you do that, what this approach is doing, it's a hypothesis generating approach rather than a strict hypothesis testing. And I think when you don't specify that clearly, it can lead to blurred lines, and then that sort of filters through then into the media, and then you get these exaggerated claims.
Okay, now I have about a billion questions, but let's start with I think the most obvious for anybody who actually wants to go and read this paper. It is the most snarky paper I have ever read in my entire life. And it was, tell us about that. Why did you write it the way that you did? And why did you try to demonstrate your hypothesis the way that you did?
We didn't necessarily think of it as snarky. I guess we were just a bit upset about people doing very simplistic analyses with these large data sets, whereas there's actually quite a good understanding of how to control for all this. So this is a well understood problem in our field, but it's not necessarily respected in lots of other ones. So maybe that was coming out a bit.
No, I think we were also sort of, I mean, the way these studies are generally portrayed, they have very media savvy, catchy headlines, such as chocolate consumption is linked with the number of Nobel Prize winners or something along those lines. And I mean, I think a good way to highlight the problems with these studies is to at times have equally headline-catching titles, such as our paper. Yeah.
And that's the thing. You took this to the extreme.
Yeah, so we were interested in whether we could find a chain of completely crazy correlations that would clearly have no causal link, but a sort of malevolent scientist might come up with crazy hypotheses about. So this chain started with acacia trees, which comes from a story. So there were two books published on language evolution roughly the same time, and this is our field, language evolution. And both covers had a picture of an acacia tree in the sunset on them, which is a sort of remarkable coincidence anyway. But actually, we looked closer, and the image was of the same tree. It was a photograph of the same tree from the same national reserve. So here was this, proof that there was some inherent link between language evolution and acacia trees. So then we looked further at this, and we found that acacia trees actually correlate with countries that have tonal languages, so tonal languages like Chinese. And then we remembered, linguistic tone correlates with certain genetic properties. That was a recent paper. And then there's a genetic correlate of political individualism, and that correlates with migration. And then we remembered there's a paper that correlates migration with the number of sounds you have in a language. And then we found another one that links the number of sounds with the amount of extramarital sex that people have in a community, and so on and so forth. And we managed to get all the way through population size, climate, linguistic diversity, traffic accidents, and finally all the way back to a correlation with acacia trees. So there's a link between all of these things. You can go out, you can get data that's freely available online from Wikipedia. You can use free statistical software to analyze it on your home laptop at home and discover these sort of scientific facts. Or that's, it appears to be what you're doing. But in fact, you're making we think you're making a big mistake by doing this.
So what is the problem? Why is it so easy to find correlations where there probably aren't any?
Well, the first problem is the size of the data set. So, I mean, these databases that researchers are drawing upon tend to be really big. And as a result, with the more data points you've got, essentially you can increase the number, or it increases the likelihood you're going to have more spurious correlations. But this isn't the only problem. I mean, what we want to say in this paper is this isn't necessarily a critique of science as a whole, and we're not saying that any scientist that does this type of paper is wrong. I mean, we're specifically looking in relation to cultural data sets. So, for example, in physics, where you have these methods that collect huge amounts of data, such as, for example, in the discovery of Higgs boson, or in astronomy, where we get spectroscopic surveys of millions of stars. I mean, these data sets are characterized by certain properties that are relatively consistent over time. They have little unpredictable variation, and the complexity is manageable. But when you then start looking at historical data sets, the amount of noise you get in them magnifies greatly through the fact that we've got the historical relatedness of languages and other cultural phenomena. We've also got borrowing across cultures and so forth. And this really muddies the data. And often with these data sets as well, again, from the internet, they tend to be incomplete. And they also weren't designed specifically for some of the hypotheses that are being referred to in these papers. So people have basically just come across this data set and say, hey, this is useful, we can look for a correlation here, and then they attribute a hypothesis to it afterwards.
So this is what I find interesting. It's basically the large amount of data that's available that makes it easier to find some kind of correlation, but we usually consider large sample sizes to be a characteristic of a good study, don't we?
Yeah, sure. I mean, but it's very specific to the type of data you're looking at. I mean, so for example, if we're doing an experiment, we've got a good understanding of the variables we're controlling for, I mean, to a certain degree. But when we come to these large data sets, the data sets tend to be collected by people unrelated to the study that's putting forward this statistical relationship. So, you've got a huge degree of people are removed to a huge degree from the original data. So when you're creating these cultural data sets, take a linguistic database, for example, you've initially got the field linguist who collects the data, and he makes or she makes a certain number of assumptions about how they collect that data, then about a particular language, and then that language is then put in the database by another set of researchers who also have their own assumptions about what sources they're going to use and what sources they're not going to use. And then eventually, after you get past the database, you've then got the researcher who uses that database to perform correlations. So as you can see, you've got this chain where the error potentially magnifies massively over time, or just through the process of way these things are constructed. And that's very different to the types of things we see in experiments, where we can accurately control and more data is good in that case.
So now this isn't, and you alluded to this earlier, this isn't specific to linguistic studies, because these kind of correlational studies are often used to bring together relatively disparate research, correct? From different disciplines?
Yeah, that's right. So that we were working on this correlation that was in the media recently between the language that you speak and your economic decisions. So if your language makes a distinction between the present and the future, then you see the future as further away, so you're less likely to save money. That's the idea, and in fact, that's what is found. So I think the correlations you find in linguistics are not dangerous because they won't affect people's lives in a massive way. But once you start applying this to fields like economics, it can get very dangerous because that research might be used to inform policy. And if the policy is based on a sort of poor understanding of the data, then you can end up with really damaging consequences.
You're listening to Science for the People, and I'm talking to Sean Roberts and James Winters about correlation and causation when researching cultural traits. Okay, so you've started talking about sort of the impact of this, because I'm wondering, how important are these studies? How much impact do they really have?
Yeah, I've just got a brief point. It's just to give one example relating to what Sean was just talking about in terms of the propensity to save money and the language that has future tense. One popular science review of the study said or suggested if you want to end the various global debt crises, try abandoning English, Greek, and Italian in favor of German, Finnish, and Korean. And even though that's slightly cheeky, it's you can sort of see the potential implications for these types of studies where you have a correlation and it gets a significant amount of media attention, and especially when you're talking about things such as economics, and if economics are looking at linguistics features and they're relating them to one another, or any sort of cultural feature for that matter, you can see how this could, down the line, affect social policy, and it can have huge implications. I mean, we see it in other areas of science where you've got the general sort of X causes cancer, where you see things like the amount of tea you drink causes cancer, or low-fat salad dressing, or burnt toast was another example I saw. Even though people often dismiss them, I mean, it can, in turn, potentially influence social policy. So I think there is an important message to the paper about the fact that some people do take these correlations seriously. And I think the ones which are maybe seem less shocking or less controversial or less media grabbing in terms of their headlines, that might seem something that we might go, hey, actually, that makes a lot of sense, but it might not have any real implications. And I think we just need to be very careful when looking at these sorts of studies.
Another point that we wanted to make in the paper, I guess the level of sarkiness was perhaps to prime people to be more wary when they encounter these correlations in the media or in science. Because, I mean, you can imagine the sort of ultimate disaster situation would be that someone with a strong prejudice, racist ideas or something, has this idea about how the world works, and then they try and prove it with these correlations. And what we've discovered is that if you can imagine a correlation, then you can probably find some sort of evidence, even controlling things relatively badly. So me and James have actually been challenged to find correlations. People have said, "Oh, surely there's no correlation between the basic word order of a language and how many children you have." But lo and behold, there was one. So and you can build stories around that. So what we want to, hopefully what the message is, just be careful of correlations. Is the theory that they're putting forward, has that been predicted by a prior theory, or are they just inventing the theory after having done the correlation? And has the correlation really controlled for all the alternative hypotheses? So other factors that you might think affect this, or the historical relatedness of the cultures involved.
I guess at this point, that's what I'm wondering is, can we put any weight in correlational studies at this point?
I think absolutely yes.
Okay.
So especially in the harder sciences, physics and stuff, like James was saying, when you have laboratory conditions and repeatable experiments, then big data sets and careful correlations are a really good thing. The problem with culture is that the methods for controlling for relatedness are not particularly well understood yet. So, but we do have some methods. So, for instance, in linguistics and cultural evolution, we borrow phylogenetic tools from biology, where we can place the languages that we have in our sample on a phylogenetic tree to control for the amount of relatedness. And maybe if we see that the correlation is all being driven by related languages like English and German and Dutch or something, then maybe our results don't really have as much impact as we thought.
Well, your paper actually suggests some methods that might provide some improvements to these kinds of studies.
One of them was what Sean mentioned, phylogenetic comparative methods, but there's also, we can build better corpora or better databases. So this comes with, and this sort of comes with people collecting more data, building bigger data sets that are better controlled. But also another thing I would like to see more of personally is building data sets to test specific hypotheses. So if you do have a hypothesis about how a particular cultural trait should be dispersed, or what it should be correlated with, then it would be good to see the researchers actually building databases around those hypotheses rather than necessarily using pre-existing databases, because then they have more control over exactly what goes in and they know the limitations of the database. Also, another thing is using independent data sets for the same or for similar type of data that can sort of provide mutually supporting evidence for or against a particular hypothesis. Another example of ways we can help control or improve these studies is having model comparisons. So we can have a null model, and then we can compare this by using random chance as a baseline, and then we can compare competing hypotheses with one another. And there's also another thing which Sean should probably talk about, which is causal graphs, which is his big thing.
So I think even if you don't have all these ideal situations like a well-controlled data set, we think you can still use correlational studies as hypothesis generating exercises. So you can maybe get a hunch from the data, but then really go and test it using other means. But rather than looking at whether one thing correlates with another, rather than looking at whether X correlates with Y, what you really want to do is put a lot of variables into something like a causal graph analysis and determine which variables affect which, but in a sort of network. What does the network of causality look like, rather than just how does one thing affect another thing?
Do you think that your paper might have embarrassed some researchers into adopting these improvements, or at least taking a bit of a sober second look at what they're doing?
Well, we hope so, I suppose.
Yeah.
We hope that this paper can sort of be used as a touchstone to get people to be more careful with their data and apply some of these techniques. They're not actually that difficult to use. There's no special program that you have to buy or anything. All this is free software, and a lot of the information that you need is freely available.
I guess it's a sort of time will tell style story, because obviously this paper is relatively new. We'll see how many citations it gets. It's certainly got a reasonable amount of attention at the moment. So, I mean, the obvious hope is that certainly in our particular fields that people will pay more attention and maybe take a step back when they're running these correlations and just think about some of the controls they can employ, or maybe even just the way in which they go about performing these studies, to just sort of take a step back and think about it.
I mean, it's not really the fault of individual academics for running these experiments, maybe, because we genuinely get excited when we find a correlation in our data. It's an exciting thing. It's like discovering gold in a gold rush. And there is a sort of gold rush sort of feel to this, because there's so much data newly available and no one's really looked at a lot of this yet. So there's a rush to discover the relationships between things. But yeah, what we hope is to sort of stem that rush for publishing the raw correlation, because it can have consequences, either being amplified by the media or being taken opportunistically by people with specific agendas to back up their own theories. Hopefully our paper will have a more measured response. We got some web coverage of this, and the news piece described our paper, and then at the end it said it was quite tickled to find that some of the things that we criticized had actually been blogged about by this author in the past. So they were a little embarrassed, and of course about the way that they had spun this in the media. But it was nice to see that even bloggers had managed to overcome our level of sarkiness and really put their cards on the table and say, sorry about this, guys. That's a nice approach.
Sean, James, thanks very much for being here.
Okay, thanks a lot.
You can find a link to Dr. Morton A. Meyers and James Winters and Sean Roberts on our site at scienceforthepeople.com. And we also encourage you to click the links to all the places we exist on social media so that you can keep up with new episodes, and to iTunes so that you can listen to past episodes, subscribe to the show, or leave a review. Thanks for listening, and we'll see you here next week on Science for the People. Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.